Friday we introduced the topic of conservation of momentum. We said that in an isolated system, the total momentum of the system will always remain the same. Now, we have to distinguish that between impulse, which says that the momentum of an object changes. But pay attention to the important words in there. The momentum of an object changes. The momentum of a system, if it's an isolated system, that is, doesn't change. Does that make sense? The momentum of each individual object. You get 2 objects or 3 or 14 objects colliding with each other. Every single one of those objects can experience a change in momentum. But if we add up all the momentum of all of the objects before the collision takes place, and then we add up all the momentum of all the objects after they take place, it's going to be the same. Individually, they change. As a system, they stay the same. Therefore, we say in an isolated system, Pi is equal to Pf. What does an isolated system mean, by the way? No external forces. So in other words, we want to look at this collision just before, immediately before the collision takes place, and immediately after the collision takes place. There may be friction here, there may be air resistance, there may be some other kind of force acting here, but if we look at it just before and just after, we're looking at it before some other external force has a chance to act, has a chance to do anything or have any effect. So we can treat it, in that case, as an isolated system. Now, we said that Pi is equal to Pf. If we have 2 objects before the interaction takes place, then we would say m1 v1i plus m2 v2i. If we have 14 objects before the interaction takes place, then we would keep going, right? 14 terms for 14 objects. Every object before the collision or explosion, remember we use that term explosion as well, even though we don't necessarily mean a literal explosion. When one thing breaks apart into 2, we consider that an explosion. Okay, we count up the number of objects we have before and after the explosion. If we have 2 objects before the explosion, then we have to have 2 terms before the explosion. If we have 14, then we have to have 14 terms before the explosion. Afterwards, same thing. Sometimes 2 objects remain 2 objects. And if that was the case, then we would say m1 v1 f plus m2 v2 f. If those 2 objects stuck together when they collided, then we would say, well, we'd only have 1 object afterwards then, so we would have only 1 term. Usually in that case, we'd say just m times vf, or mt. What would mt stand for? The total mass times Vf. So if they bounce apart, you're going to have at least 2 objects afterwards. If they stick together, you're only going to have 1 object afterwards. Usually it's one of those 2 situations. 2 objects either bounce apart or stick together. But understand that there could be more. There could be 3, 4, 5 objects conceivably, although that doesn't usually happen. Like, don't memorize exactly what you see here. Like, look at the situation, count up the number of objects you have, and put a term in for every object. And it shouldn't be that hard. All right? Plug in your numbers, solve for whatever variable you're looking for. One final thing, and then we'll check over those 5 questions that we had for homework here. We said on Friday that we could conceivably use for velocity, let's say, kilometers per hour. Or we could use for mass, we could use grams, or even milligrams, or micrograms, or something like that. Why can we use, for this concept, conservation of momentum, but not for other concepts, why can we use whatever unit we want, really? Yep? Because the units cancel. Right? The units appear in every term. As long as you have the same units through every term, then the units cancel, and it doesn't matter what you use. If that confuses you, because usually we have to use meters per second, right? And we have to use seconds and meters and kilograms. If that confuses you, that in this case we can use whatever we want, then just use the standard units. You got kilometers per hour, you don't like that, just convert it to meters per second and go with meters per second, because that always works for us, whether it's this or any other concept. We're going to go over questions 1, 2, 4, and 5 from worksheet number 3. Number 1 says a 2.5 kilogram ball moving at 7.5 meters per second is caught by a 70-kilogram man while the man is standing on ice, how fast will the man/ball combination be moving after the ball was caught by the man? This conservation of momentum thing is one of those situations where we can always do something, right? We've seen a few of those already this year, right? We've see on the board here in the top left corner, when we see an angle, okay, we always think, I don't like funny angles. We take it off to the side, we get rid of it. When we see force and time in the same question, we always think impulse. When we see a force versus time graph, we always think, area equals impulse. And now, whenever we see a collision, that's a collision, okay, or we see an explosion, not literally necessarily an explosion, but where one object splits apart into two, whenever we see one of those things, we think conservation of momentum, PI is equal to PF. It's exactly what we have here. It's exactly what we should be thinking here. Okay? We shouldn't need to see the words at the top of the page to tell us that that's what we're going to do for this. All right, so let's write down some givens for this, knowing what we're going to do. We're going to say M1 is 2.50 kilograms. And I'm going to say something, V something is 7.50 meters per second. We're going to call that V1 or V2? Good, that's V1. That's V1. Is that V1I or V1F? It's V1I. We got to make sure that we put both subscripts in there, right? V1I, V2I, V2F, whatever it happens to be. We got another object here. We're going to call the second object, the man, 70.0 kilograms. And we're going to say, do we have anything else here? I don't see any more numbers. Do we have anything else, Danny, if we read between the lines here? Good. V2I is 0 because the man is at rest. What are we looking for here? What is it that we're looking for in this question? What is it, Nick? Yeah, we're looking for VF, and that's all we're going to call it is VF. Not V1F, not V2F, because there's only one velocity, because they both, the ball and the man, head off together as one. So let's say PI equals PF. Remember that we could look at this as impulse, but if we did that, we'd have to look at either the impulse of the man or the impulse of the ball and not try to combine them. Do one at a time. We're going to do conservation of momentum for this. Two terms before the collision takes place, M1 V1I plus M2 V2I. Two terms, two objects. Or sorry, two terms because we have two objects. Now, they stick together or they combine, so what's the final term going to be here? What's the final term going to be? What are we going to do for that? Yeah, we're going to say MT, mass total, times VF. Now, if the masses were the same, we could cancel them. That's not going to happen when we're combining masses, right? Let's sub in some numbers in. 2.5 times V1I plus 0 equals, the total mass here is 72.5 times VF. So 2.5 times 7.5, and then divide that by 72.5 gives us 0.259 meters per second. I should have asked you for a prediction as to what we were going to get. We got a much smaller number for velocity than we started with, right? How come? Why is it, not only is it smaller, it's a lot smaller than the initial velocity of the ball. Why? Yep.
Because the man weighs so much more than the ball?
Yeah, the total momentum stays the same. Okay, the man and the ball have the same momentum as the ball had initially, but the man weighs so much more that in order to get the same momentum with a lot more mass, you have to have a lot less velocity. Are we good at that? Who asked for number one? Is that good? How did I get 72.5? This is the total mass, which is the mass of the man and the mass of the ball combined, right? Because he catches the ball, so he becomes one with the ball. Okay? Two, 1,200 kilogram car traveling north at 20 collides with a 1,400 kilogram car traveling south at 22. Two cars collide and entangle. What's the resulting velocity of the wreckage? What am I going to do first here? Very first thing, what am I going to do? Kyle? Yep. Pull with the red pen. Identify that we got north and south here. This is not the mistake we want to make. Okay, this is not the mistake that we want to take us from 100 to a 98. Identify that we've got north and south. That means that, well, we'll say that M1 is 1,200 kilograms, and we're going to say that V1I is positive 20 meters per second. Positive because it's to the north. We're going to say that M2 is 1,400 kilograms, and we're going to say that V2I, the initial velocity of car 2, is moving at negative 22.0 meters per second. Hey, Kyle is definitely not going to make the mistake of making that positive, because first thing he thought of was to identify, to draw attention to the north and south. They entangle and collide. We're looking for VF here, the final velocity of the combined wreckage here. So once again, we could do impulse if we looked at one object or the other, looked at them separately. We're going to do them together. We're going to look at the system here. So we're going to say PI equals PF. M1 V1I plus M2 V2I. Two objects before, two cars before the collision, two terms in my equation. They combine, they collide, and entangle. They become one. One object after the collision, one term in the equation after the collision. Masses don't cancel. We're close, but not close enough. So we're going to say 1,200 times 20 plus 1,400 times, Kyle? 1,400 times negative 22, because it's south, right? Equals MT times VF. M2, MT times VF. What's the value of MT? What's the value of MT? Yeah, we're going to say it's 2,600. Both cars combined times VF. So get this number, and then you're going to subtract them, right? Because you're adding a negative number. And then you're going to divide by 2,600 to get VF by itself. And when you do, you get negative 2.62. When I gave you the answers a few minutes ago, I said negative 2.62 or 2.62 to the south. Really, we should define north as positive here at the beginning of the question, but like unless you're defining something in a way that you don't normally define it, we don't have to write that anymore. Okay, it's okay just to assume that north is positive and south is negative. Next question we want to look at, number 4. A 1,500 kilogram car traveling 100 kilometers per hour south collides with another car traveling north at 100. The heavier car continues to move south, slows to 25. How fast is the lighter car moving after the collision? What's the first thing I want to do here? Circle what? Yeah, the direction here. North-south thing. South, north, south. You might even want to draw attention to this. Just because usually we don't want kilometers per hour, although in this case we can do that. Yeah, I'm going to do it actually in kilometers per hour this time. Although you can, of course, you can do it in meters per second as well. We're going to say M1 is 1,500 kilograms. We're going to say that, what is this, 100 kilometers per hour? What is that? V1 or V2? Matthew, V1 or V2? Or, yeah, V1 or V2? V1, good. Is that V1I? Gage, is that V1I or V1F? Good. V1I, the initial velocity of object number 1. Is that good? Is that right? It should be negative because it's to the south, right? And you could convert that to meters per second. I think it works out to be negative 27.777 meters per second if you do that. We're going to say that object number 2, M2, is 1,200 kilograms. And we're going to say that V2I is, this one is also 100 kilometers per hour, but this one's to the north. So this would be converted to meters per second, it'd be positive 27.777. But again, the units cancel, so we can leave it kilometers per hour if we want. The heavier car, which is car number 1, moves at 25 south afterwards. What's that going to be? What is that? Is that V1 or V2? V1. Yeah, it's V1. And it's V1F. V1F is negative 25 because it was to the south. And we want to find the lighter car. We want to find V2F. PI equals PF since we're analyzing the system. Now remember that when we find the velocity after the collision, like we're finding the velocity not 3 seconds after the collision, right? We're finding the velocity like right away after the collision, before there's any external forces, while we still have an isolated system. 2 objects before the collision, 2 terms in the equation. 2 objects after the collision, 2 terms in the equation. Let's say 1,500 times negative 100 plus 1,200 times positive 100 equals 1,500 times negative 25. Again, you could be in meters per second if you want here. Plus 1,200 times V2F. We'll go through this one together on the calculator because there's quite a few terms in there to deal with. Let's say 1,500 times negative 100. Okay, there's my first term. Let's add to that. Now I'm going to use some brackets here so I can multiply 1,200 times 100. There's my left-hand side. There's my left-hand side. And now I want to take over the 1,500 times 25. I'm going to take it over by adding because I've got a negative number over there. I'm going to add 1,500 times 25. Does that make sense what I've done there? And now let's divide that by 1,200. And we get 6.25. V2F is 6.25 kilometers per hour. Positive north. Or what do we get in meters per second? I think it was 1.74 meters per second. Yep, Daniel?
I'm confused as to when to use MT, VF, and when to separate them.
Okay, when do we use MT and when do we separate them as M1 and M2? Whenever we have an object, okay, whenever we have an object, before or after, we have to have an MV term for it. Okay, does that make sense? So if you have an object, we have an MV term for it. Now, if that object is at rest, we could, if we wanted to, just drop that term because its momentum would be 0. Okay? But if you want to still include it, go ahead, just sub in a value of 0 for velocity. But essentially, whenever we have an object, we have an MV. Now, in this case, before the collision, we have 2 objects, 2 cars. There's the light car and there's the heavy car. So we have 2 terms, MV and MV. But we just put different subscripts, object number 1, object number 2. So does that make sense? Now, to answer your question, why do we sometimes have 2 terms afterwards? Why do we separate them? And then sometimes why do we just make it MV afterwards? If they stick together, if 2 cars collide and then somehow the metal becomes entangled and they go off as one object, or if you throw a ball at me and I catch it and me and the ball go off together, one object, we're only going to have 1 term because we have 1 object, right? But remember, that object is heavier now. When I catch the ball, me and the ball, let's say I'm 70 kilograms, the ball was 5 kilograms. Now me and the ball go off together at 75 kilograms. But if the ball bounces off me, then I go off with 70 kilograms and the ball goes off separately with 5 kilograms. So if they stick together, we just make it one term, m total times VF. But if they bounce off of one another, then they're still separate from one another, so we have to have two terms and keep them separate.
How do you know that these two, like, would they have to indicate that they stuck together? Because I would have assumed that they went off in like the same.
Oh, okay, I see what you mean. Yeah, like unless it says they stick together or entangle or something that means the same thing as that, then we would assume that they bounce off of each other. Okay, so a question like this that doesn't actually say that they bounce off of each other, if they did stick together and we assumed they bounced off of each other, like let's say they did happen to stick together and we just didn't know that. What final velocity for car number 2 do you think you would have gotten? 25 kilometers per hour. Right? You would have solved for V2F and it would have worked out to be the same as the other one. So it's okay to make them separate if you're not sure. It'll work out. Okay, that makes sense? But don't make them the same. Don't make them stick together unless you're sure they stick together. Okay, good question. Okay, finally, number 5 says a 92-kilogram football player running at 6.5 meters per second to the north collides with an 85-kilogram football player running at 6 to the south. Continues moving at 2 meters per second. What's the velocity of the 85-kilogram football player after the collision? You know what? I think actually for this one, who asked for this one? Okay, did you ask for number 4 as well?
Yeah, I was just mixing it up and not splitting them out.
Okay. I think I'm going to leave number 5 right now because it's real similar to question number 4, right? And I'm going to ask anybody that had trouble with number 5 to give it another shot based on having gone over the last 3 questions here. And if you have trouble with it, let me know. We'll go over it. But hopefully now we've done enough where you're going to be able to do that yourself.